Why don't we get started? Are you ready?
Yep.
Okay, great. All right, so it's great pleasure to introduce Abraham Vinod, who is a research scientist at MERL, Mitsubishi Electric Research Laboratories. Abraham has received his BS and MS in electrical engineering at IITM, the Indian Institute of Technology, Madras, and then he received his PhD at the University of New Mexico, I believe, under the advising of Miko Ishii.
Yep.
And after that, he was a postdoc at UT Austin, and after that, he joined MERL, where he's doing great work. I was there for a few weeks last summer. I enjoyed very much the interactions. So today he's going to be telling us about some of his research interests on motion planning, but he also has interests on many things, including learning, decision-making under uncertainty, in particular for autonomous systems. I should add that he also received the Best Paper Award at the 2017 ACM Hybrid System Computational Control, and also was a finalist for the Best Paper Award at the 2018 ACM Hybrid Systems Computational Control, and that his MS thesis from IITM received an award called the Professor Akim Prize. So with that being said, Abraham, we are excited to hear about your talk, and the floor is yours.
Thank you so much, Ricardo, for the kind introduction, and thank you so much for the invitation as well. I'm excited to give this talk. In this talk, I was kind of hoping to give you guys an overview of my research into motion planning problems under uncertainty, and I'm happy to have any questions or discussions as we go through the talk. Feel free to interrupt me. So to get things started, what I thought we should do, I have a pop-up in my Zoom. Okay, that was because when I said that. Sorry. To get things started, what I wanted to kind of emphasize, and this is something which you guys already know, is that autonomous motion planning is quite important in a variety of applications. We have already seen its impact in applications like robotics, transportation, and space. So three motivating applications that I want to kind of highlight in this talk is shown in these three figures. One is sort of the need for fast and resilient multi-agent motion planning. This could, for example, come very handy when we have multiple autonomous systems navigating an intersection, or for example, in factory automation, where you would have drones that would be coordinating with each other while they transfer packets here and there. A second problem that I want to kind of talk about is the need to accept the fact that control on its own is not the end solution. We need to constantly interact with other modules like perception and sensing. And naturally, these sources of information are not always abundant. While these computing systems are becoming more and more powerful, there is definitely need to account for the fact that these computations take time. So we also would like to investigate motion planning when sensings are constrained. And that's what I'll probably touch in my second part of the talk. And the third part of the talk is the need to make sure that whatever planner that we generate is resilient. By resilient, what I mean is, in an example of like spacecraft rendezvous, when we're autonomously trying to dock with a spacecraft, in case of an event of a failure, for example, an actuation failure, we would like our motion plan to be such that we can abort safely. So we need to have a component of graceful degradation baked into our motion plan. And this will allow us to ensure that the entire autonomous system stack is resilient under unexpected failure. So all in all, what I'm hoping that I can get you guys excited on is that we need fast motion planners that can navigate cluttered environments where there are a lot of obstacles, there are other agents that are acting in the environment, and we want to move in this environment safely, despite various sources of uncertainty, some coming from the sensing limitations, others coming from the simplified models that we need to do fast motion planning. And together, we want to generate these plans such that we also account for the possibility of failures, and we do not cause more issues when a failure occurs, and we can stop prematurely. And my proposal is to use data reachability and constraint control theory to solve this problem. That said, I have not solved the entire problem yet. This is very much a work in progress, but I can give you different directions that I've pursued, and hopefully I would love to hear your thoughts on if there are things that I can do better or we can collaborate on. So to give an outline of my talk, I'll start with the Merle overview. Since as Ricardo said, you guys have already probably heard of it, I'll maybe skip through things a bit faster. And then the first part of the talk, I'll talk about safe RL-based multi-agent motion planning. Here, we basically try to ask the question, can we leverage learning to do safe multi-agent motion planning? And I'll have some nice demo videos that we did with our experimental validation using crazy flies. And in the second part of my talk, this is my work that came out of my postdoc, where we did safe motion planning under uncertainty when the sensing is constrained. And this, again, we were able to validate nicely with turtle bots. And what we were trying to aim for is when we have very limited access to sensors, how do we sense obstacles so that we can reduce the uncertainty while planning in a cluttered environment? And finally, if time permits, I want to also touch upon this about safe spacecraft rendezvous problem, where we are trying to dock with the spacecraft autonomously while always ensuring that we can divert away safely in the event of a failure. All of these solutions will use a combination of data, reachability, and constraint control theory. And that's why I feel like these three are crucial ingredients to allowing safe autonomous planning. So to get started, let me give you a quick overview of Merle as it is. We are an open research lab. We are a research division from Mitsubishi Electric. We work on problems varying from factory automation, robotic space applications, and including signal processing. So we have around 54 researchers split across multiple groups, and we collaborate internally as well as with academics outside. Ricardo, for example, has collaborated a lot with us, and we look forward to having other collaborations as well. This is my group, Control for Autonomy. We are led by Stefano, and we are around 7 researchers. And then at the high level, what we're trying to aim for is coming up with solutions that exploit structure in a problem to allow autonomous systems to be more capable. We would like fast, scalable, and real-time implementable solutions that can tackle a variety of tasks an autonomous system may be tasked with. We are actively collaborating with a bunch of collaborators as well, and a lot of the problems that I'll be talking today were actually, in fact, either started off or ended with more and more collaborations. So we have a lot of interns that join us during summer, and they are kind of organically grow into collaborations with academic partners. The target areas of our group started off with vehicle autonomous driving systems and space applications, and have since diversified into electric systems, connected cars, and drones and legged robots. We are quite open in the research topic, and because we get most of our research problems either from Japan or from a creative group within us, we can work on a variety of problems. And we do have expertise, and we do look out for expertise in the variety of topics like this. And we are constantly trying to stay and learn the state of the art so that we can further help our colleagues back in Japan to implement these in our products. So to give you a flavor of the various research areas that we work on, we have topics including and not limited to advanced motion model predictive control, safe constraint control, statistical estimation, integrating learning and control, as well as real-time optimization algorithms. So we build both theory and algorithms to tackle a variety of these topics. And we have most of our problems are always motivated by an application. So we would typically have a problem that would need a bit more research than what the state of the art allows. And that's when we either initiate the research on our own or reach out to collaborators to help us solve the problem. We also have a variety of evaluation and test platforms, including drones, which I'll show you a couple of videos today. We also have legged robots, as well as autonomous cars, as well as hardware in the loop. So all of these help us to validate whatever prototype solutions that we build at the lab as well. And this is the last overview slide I had. What I want to kind of emphasize is we have a new postdoctoral research fellow program. So please let us know if you have any candidates of who you think would work well in these topics. I'll be happy to talk more. All we need is a research statement of around 2 pages long on kind of giving them a direction. What they will get is a 2-year stint in working in industry, which will, while allowing being able to publish and collaborate with internally as well as external to other academics as well. And this is a new program that we are quite excited about. We also have internship opportunities. Typically, our summer internship postings come later in the winter. But right now we have one posting open where we're looking for a student who's expert in hardware implementation of some of the algorithms. More details you can see on our website. All right, so now let me get into the meat of the talk. So the first topic that I'll talk about is the safe multi-agent motion planning using filtered reinforcement learning. So this was work done with my colleagues at MER, as well as an intern, Sulaiman Safoi, who's at UT Dallas with Professor Tyler Summers. So to motivate this problem, what we are interested in is developing efficient solutions for multi-agent motion planning. As I said before, we have a variety of applications that need such solutions like factory or warehouse or urban mobility, as well as autonomous traffic management. And what we're interested in is to see if we can leverage learning to speed up safe motion planning. In general, these motion planning algorithms, because of the multi-agent aspect, require a lot of computational effort. And we are hoping to see that we can use learning to essentially alleviate some of these problems, as well as make these motion planners more richer. So as you can expect, multi-agent motion planning is an active area of research. There has been a variety of solutions proposed for a variety of tasks as well. What we have recently observed is learning-based planners, they can use the history to make decisions into the future. This can come very handy in problems where you have information coming from visual images, or for example, policies that are deep, and that can help, for example, in problems which require a complex task description. However, safety in general for these problems is a big issue because we typically have to rely on function approximation. And in single agent systems, there have been a couple of solutions. Notably, there is a barrier functions-based approaches, or where you define a function that kind of filters their actions based on this perceived possibility of safety. Alternatively, there's a fielding approach where two-player games typically solved offline to identify safe actions at every instant, and then with the controller that the learning module prescribes is overwritten whenever it's unsafe. And there's also more recently a predictive safety filter where MPC-like ideas are used to correct for our actions. Our approach that we are proposing, it basically takes the predictive safety filter-like approach and extends it to a multi-agent system and accounts for the stochastic uncertainty. So in this part of the talk, what I'll kind of propose is a method to do safe multi-agent motion planning in stochastic and cluttered workspaces, where we use reinforcement learning to learn from prior data, and then use set-based control and convex optimization to achieve safety. So as an overview, the safe multi-agent motion planning will use the combination of RL and constraint control theory. We'll use RL to define the high-level tasks. So tasks like reach a goal or do task allocations such a way that some other objective is met. And this problem, giving the entire motion planning problem to RL will not give safety. Additionally, it will be harder to train a policy. So we split the tasks into a high level and low level, where problems like avoiding collisions will be given to an optimization-based safety filter. So as a flow chart, like we have basically the RL module giving us a candidate trajectory as action, and then a safety filter block that takes these actions to then make corrections so that the underlying system is safe. At a high level, you can see that if there, for example, RL makes the agent go like these two agents go like this, which will result in a collision, the safety filter will come up with these corrections that will ensure that the resulting motion is collision free. So why do we care about this combination? One, by training our RL agent to be single agent at this point, because we have decoupled the problem into a high level and low level task. A single agent solution is typically easier to train compared to a multi-agent solution. Additionally, by using the safety filter, we can then tackle the non-convexities that arise with an optimization-based planner alone, because these problems will require to solve collision avoidance constraints that are non-convex. And finally, we will observe that the combination together gives a scalable as well as a real-time implementable solution. So let me quickly go over the two steps. So the RL block as well as the safety filter block. So in the RL block, the way we have tackled this training problem is to kind of define a double integrated dynamics for the quad rotors that would be our robots that will be moving in the factory. We basically require a specification of a reference target, which then using the double integrated dynamics turns into waypoints, which we give then to a low-level controller for the quad rotor to move. So the action in this case will be the reference target. So for the single agent RL problem, we have an observation space that is defined and sort of the position and the velocity of the agent in this dynamic space. And then additionally, the displacement to the target and then displacement from the static obstacles, NO of them. Because this is single agent, we don't have to worry about the agent-agent collision avoidance in this case. And therefore, we have much lower number of dimensions compared to the case where we have to solve it in a centralized manner. The action space in this case would be the reference target, as I said. So the RL agent would prescribe the reference target for these drones to follow. And then finally, we have the transition function and the reward function geared towards making this reference planner work in the direction that we want. On the safety filter side, we then compute a corrected input controller that will make the system probabilistic collectively safe. So what I mean by collective safety is that we want to ensure agent-agent collision avoidance, agent obstacle collision avoidance, and also to stay within an operating region. So at the safety filter level, we'll be solving a problem that looks like this. So we would be getting the RL controllers at each time step, and then we'll be computing the minimum corrections required so that we satisfy the collective safety. Additionally, we have terminal constraints to ensure recursive feasibility because it's a model predictive control style solution. And we have to then solve this problem for the safe controllers, which we will then apply. So naturally, you would say this is not an easy problem to solve. This is a non-convex solution problem. So the way we tackle this is by convexification. So for example, for the keep-in constraints, we come up with a constraint tightening where we can take in the original convex constraints in this case for the keep-in constraints and then tighten it so that we have a sufficient condition to satisfy the stay in within operating region. Similarly, for the agent-agent and the agent obstacle collision avoidance, we do the constraint tightening, but after doing a convexification step. So for example, if we have to do collision avoidance between these two agents, we, in one of the relative coordinate frames, like here, or in this case, sorry, here, we want to ensure that this agent stays outside this bigger circle. So by considering a supporting hyperplane and then subsequently tightening it, this green area is a sufficient condition, sufficient region for the second agent to stay in that will allow us to guarantee collision probabilistic safety as we desire. So by doing this convexification, what will end up happening is this problem will be reformulated as a convex quadratic program, which we can solve very quickly and allow us to come up with safe controllers originating from the RL controller and having minimal deviations. And this is what we can then use to the system and give it to the system. So there are a lot of questions that is hanging around here. Like, is the safety filter really necessary? So to answer this question, we did a validation where we took the RL-based controller without uncertainty, and then asked it to go towards its target from different starting locations. So what I'm showing you in this leftmost plot is the RL controller, without the uncertainty, where we have this green region, which is this region where it reaches this target, and the orange is the region where it actually ends up colliding. So as you can see, without the safety filter, there are a lot more regions where it collides, and whereas with safety filter, it almost disappears. This too is a case where there is no uncertainty involved. And then additionally, when we add process and measurement uncertainty, we get a slightly different result where now, because sometimes uncertainty could help you, sometimes it could hurt you, but with the safety filter, again, we get much better performance. There are some places where if you start from there, the safety filter is not able to recover from a deadlock, but at the same time, it will always guarantee safety, which cannot be guaranteed using an RL-based controller on its own. So all in all, we can say the safety filter improves the generalizability of the RL-based controller. And then the other question is the RL component necessary? So then for this, we can compare this with a pure MPC-based solution, where we directly asked to solve a centralized solution and then compare the performance of approaches. So what we observed is that when we use a pure MPC solution, first of all, the terminal constraints are quite conservative, and it breaks down the MPC solution from the get-go. However, when we relax a constraint, there are 55% of the time where it actually works. Whereas when you use the RL-based solution to do the warm starting, if you will, we get much higher success rate. That said, because the RL-based controller is a single agent controller, which is then coordinated with safety filter, it is more suboptimal compared to the centralized solution, which is expected. So there's a trade-off that will always happen because we are breaking the problem into two parts and then solving it independently. But the key takeaway is that with the RL-based controller, we actually have a significantly larger success without a much number of deadlocks or collisions. So then to kind of do this experimental validation, what we did is show this, test this using crazy flies. So on the right, you'll see the actual experimental validation. On the left, you'll see the reconstruction, where these shaded polytopes will actually be the regions, the stars are the targets, the black circles are the obstacles, and then this the flyable region. The shaded regions are the obstacle-free regions. So as you can see that drones are able to negotiate with each other. Remember that they are all originally are started with a single agent RL controller, which doesn't know any of the agents, where the agents are, or doesn't care about them. The safety filter takes the responsibility of maintaining safety in those cases. And the RL controller is what prompts the drone to go towards its target. We also did the experimental validation of the RL being necessary component. So where we replace the RL controller with a simple proportional controller for warm starting the solution. And this is how the results work, how the experiment works. So while the RL-based controller is able to, because it was trained on prior data, it's able to complete the task much faster. Because the proportional controller always guns for the target, it gets stuck in front of the obstacle, and the safety filter has to take it, push it either side to kind of go around it. And as you will see, there is one of the drones that actually does get stuck in a corner there because it's trying to get over here, and this is like a pocket of sorts. So before I conclude this topic, I also want to kind of highlight this approach does scale well because we have a single agent solution that's kind of replicated across agents. And the next steps that we are going to pursue is to look at a decentralized formulation of this, where we don't have a safety filter that prescribes everyone's actions. And we also are looking into how can we relax the Gaussian uncertainty that we currently have in this approach. So this work is already published in ICRA, and we have a TRO paper under review. The key takeaway I want to have with this part of the talk is that we can construct safe multi-implementable, real-time implementable multi-agent motion planner using reinforcement and constraint control. So before I go to the next part of the talk, are there any questions?
I have a quick question.
Yes.
So when you implement this, or in other words, is the RL run offline, and then you implement the policy that you learn offline on a model?
So the RL training is done offline, but the RL policy is evaluated online. So we wrap the whole thing in a receding horizon solution. So every instant we look at where we are, ask the RL policy to give us a sequence of control actions to take, and then the safety filter corrects for it. Does that answer the question?
Yeah. And so RL, I guess, if I understand correctly, the learning occurs offline, but online you calculate the policy.
Yes. Yeah. So that's our preliminary approach. You could, I think, are you kind of hinting towards why not do the learning online?
No. I'm trying to understand the setup, because when you say implementable here on the screen, real-time implementable, if you were to do online RL, that would be thoroughly challenging, implementably, computationally expensive, right? I mean, I was wondering, have you considered online?
No, we have not. We're also worried a bit about the fact that with online RL training, we also might have this policy instability that might happen, where as we keep on training, suddenly some data can throw the policies parameters from its current local minimum. In which case we cannot really, we don't know how to account for that in the consequent down the stream, essentially. So long story short, we have not yet tried the online aspect, but that's something that we could try.
Thank you.
I have a question.
Yes, please.
The first question is like, what do you mean by the cluttered example environment?
So by cluttered, I just mean that in an environment where we have a lot of obstacles, and we have to be careful on how we move.
Like the number of obstacles? Like
yes. Yeah.
Okay. My second question is like, what I mean in the safety deadlock, the simulation result, like what the RL with safety filter, like why RL with safety filter can avoid the safety deadlock? Like is there any like particular design about it?
Not necessarily. I think it's more to allude with this fact. So on the like, I will ignore the uncertainty aspect for now. When we don't have any uncertainty, if you directly evaluate the RL controller from different directions, you can see that even behind this obstacle, the RL is able to learn to go around it. There are some places where it'll not generalize well and it'll hit the obstacle. But these green regions are the areas from which, if you start the drone from, the RL policy and only follow the RL policy, it is able to reach this target. So this is what really helps us stay different from a baseline controller where we only gun for the target. So in other words, the prior data and learning from it helps us do a better convexification.
I have another question. Did you discretize the region for reinforcement learning calculation? And if you did, how did you choose the cells based on safety and dynamic of the system?
So we actually did not discretize this one. We actually learned the continuous state space RL model. So we used PPO in this case for the RL training, which can accommodate continuous state space and continuous action space. All right. If there are no other questions, I will move to the next part. Thanks so much for the questions. All right. So in the second topic, this is a work that I did during my postdoc with Ufuk Topsku and his students. This work was primarily done by his student Michael, and we both collaborated on the stochastic aspect. The high-level problem that we are interested in this part of the talk that I'll talk about is motion planning when we have uncertainty and when we are constrained on what we can sense. So to kind of sketch this picture, what we typically have is existing perception and sensing-based controllers assume that the perception is great, and we have access to a lot of data coming in, which allows us to actually do motion planning in the environment. But in reality, perception is heavily constrained. There could be perception failures. There could also be the fact that the computational resources are limited. So for example, in the case where I have a drone that has to fly from here to here, in reality, it doesn't matter, even though these obstacles are here, the uncertainty typically means that we have to think of as a virtual obstacle, a much larger obstacle to avoid. So that's what I mean by these shaded areas. But regardless of all of that, this drone, if it has to move from here to here, in reality, it only needs to care about the green circle. As long as we know, or if we can reduce the green circle, the uncertainty around this obstacle, we can, in effect, generate a better motion. And that's what we were trying to encapsulate in the theory and an algorithm in this approach. So in other words, how do we design a safe trajectory for a robot to complete a task under uncertainty, where there would be things coming from sensing as well as process noise, while reducing the uncertainty via sensing, but acknowledging the fact that the sensors are limited. So specifically, like at a high level, this problem with when there's full obstacle information, there's again a lot of work using particle-based approach and chance constraints, as well as using successive economy explanation. But what we are interested in this problem is when we have requirement that a robot can sense only a fixed number of obstacles at every time step. How do we account, or do we decide which obstacles to sense, and how do we account for that degree of freedom into our motion plan so that together we'll always be safe. So when we make this restriction, so essentially we are working on this partial information setup. There are some works that work on like caution belief spaces as well as active perception, but they don't encapsulate this constrained sensing aspect fully, where we have to simultaneously do sensor allocation as well as motion planning. And what we would really like is to be able to sense only those obstacles that are really relevant to the trajectory. And what I'm going to propose is a way to kind of do that. So this is the problem setup that we have. We have a world where our robot is a nonlinear dynamic, has nonlinear dynamics, but it's controlled. We have obstacles which have stochastic dynamics, but it's uncontrolled. Stochastic basically because we'll assume that the sensing measurements allows us to build a Kalman filter for every obstacle. And they'll keep on updating this Kalman filter depending if and when we sense an obstacle. And given this setup, we have to do solid motion planning where we minimize some objective that is a function of the robot state as well as control, while ensuring that this collision probability is less than alpha. So in this, to make things simple, what I mean by this collision probability is that the probability that our obstacle state lies inside a ball around the robot, that probability is less than some very small number alpha. So if that is holds, then we have a safe motion plan. So we now need to solve this motion planning problem and then simultaneously decide a sensor allocation that decides which obstacle would I observe in the next instant. And only when I observe the obstacle would I get any information for the Kalman filter. Otherwise, I will just use the Kalman filter's prediction steps, which will have ever-growing uncertainty to then feed into my motion planning problem. So this is the setup that I'm going to work. So there are a couple of key insights that we did, and I just want to kind of highlight that, and then I'll show you the experimental validation of this approach. So the first is, how do we compute these collision probabilities? In general, this collision probability is a multi-dimensional integral, and it's hard to compute accurately. So what we did was use one of my previous results, where if you want to avoid hitting an obstacle with a high collision, high probability, according to the fact that the obstacle has a rigid body and I have a rigid body, in this work, in the attack paper, what we showed is that it's equivalent to avoiding a Minkowski sum of a specific level set of a Gaussian that describes the obstacles information grown by the rigid body. So this gives us a nice result that looks like this. So if I have a collision avoidance probability constraint like this, then I essentially have to stay outside a different ellipsoid, an ellipsoid which has the same shape as the covariance of the Gaussian, and centered about the mean position of the obstacle, and everything is easily available or easily computable. So in effect, this collision avoidance constraint, which is a hard non-convex constraint to solve, becomes a simpler, still non-convex constraint, that is to stay outside an ellipsoid, where these ellipsoids are easily computable. So this is a first insight that we have used. The second insight is, now that I have replaced this constraint with an ellipsoid, avoiding an ellipsoid, we still have to contend with the fact that we have a non-convex collision-free constraints as well as non-dynamics. So we start out off with using a sequential quadratic programming solution to find a local optimum. So in case you're not familiar, sequential quadratic programming essentially linearizes the dynamics and the constraints, and then repeatedly solves it until convergence or until a stopping criteria. So in this case, we took these collision avoidance constraints and converted into separating half-space constraints. Similarly, linearized constraints, and additionally, we linearize the dynamics as well and keep on solving this again. So because this is now a quadratic program, it's much more faster to solve, and we get a local optimum. The local optimum is a very loose term here. We might actually be suboptimal very bad, poorly, but at least we can hope to achieve a feasible solution. But there is also another observation that we needed. The thing is, by solving an SQP problem on its own, because we are linearizing the constraints, we typically end up with a situation that looks like this. So even if these obstacles are over here, because of the linearization, in effect, our solution would be requiring that we stay to the right of this region, which means we would be heavily conservative. So going off of this work from Bechet Akme's group at University of Washington, what we also did is a project and resolve approach, where once we get this approach, once we get a solution to the sequential quadratic program, we then projected the solution back onto the obstacles to kind of enlarge this collision-free space. So the way I like to think about this is, if you're walking in the dark with your eye where you can't see, you would reach out with your hands to figure out where the obstacles are. That reaching out with the hands is essentially what we're doing in this projection step. And with this collision-free, with this larger space, if you solve, if you go back to our SQP sub-problem, we have to we replace this constraint with supporting half spaces now, as opposed to the linearization. And what this gives us is two benefits. One, it just allows us to polish the last solution to hopefully make it less conservative. And additionally, it allows us, as a byproduct, a sensor allocation. What we are using in this case is a sensitivity analysis result, which says that the dual variables of an optimization problem allows you to account for how the objective would change if I change some of the constraints. So in other words, when an optimization problem that looks like this, the dual variables associated with this constraint tells me, the lambda star tells me, if I change delta, how much will my optimal objective change? And that's exactly what we need in this case. In other words, when we solve the project and resolve problem, we look at the dual variables to decide which obstacle is most affecting our trajectory. And then we pick that to sense. And because of this, we will automatically get back to the intuitive solution that we had in the beginning, that we only need to sense the obstacles that really affect our trajectory. So as I said, we want to measure the obstacles that would have the greatest impact on the performance. And the way we do it is by considering for each obstacle a future discounted sum of the dual variables, and then pick the obstacle with the largest sum, or pick the k number of obstacles with the largest sum, depending on the sensor. So to tying it all together, this is the problem. And the way we solve it is in these three steps. So first, we use stochastic feasibility to compute an efficient and tractable collision-free sets. And then we use SQP and a project and resolve in the last step and then finally decide the sensor location. So using the dual variables. So we did also an experimental validation of this approach, where we tried to navigate this robot from here to here, where with the presence of 3 obstacles. On the right, you will see the reconstruction of the experiment, where the reds currently indicate that its uncertainty, and you'll see it grows whenever the obstacles are not sensed. Whenever we sense it, you'll see it in blue. And the way we sense it is by using a camera on the robot, where whenever, because each of these obstacles are color-coded, whenever we decide or whenever we see this color on the camera, we then query the motion tracking system to give us a true estimate of the position. Otherwise, we don't have any position estimates, and we just keep on using the Kalman filters prediction steps to do the motion planning problem. Let me play this video. So initially, because this agent's uncertainty kept on growing, we turned towards it to view it, and then whenever we have agent obstacles uncertainty affecting our trajectory, we keep on viewing that to kind of mitigate the uncertainty. Here, as you saw, this uncertainty grew too large, and then we sensed it, and then we stopped sensing. So we never sense the agent obstacles which don't come into our purview of our trajectory. So since obstacles are far away or which does not affect our trajectory, we do not sense it, and you only sense those obstacles that are important. And because we are using SQP in this case, and because of current advances in the computing solvers, this again allows us to do this planning in real time and account for this perception block as well. And this is the computation time currently that we on a standard desktop. So before I kind of wrap up this topic, we also tried other approaches and also did some comparisons with the Gaussian belief space motion planner. But for simplicity, I'll just talk about the other different sensing approaches that you could take. So this is the safely is our approach that we said. Alternatively, we could sense the obstacle with the largest uncertainty. We could also sense the obstacle which is the closest, and we also could do a round robin sensing where we sense every obstacle. What you will notice is that our approach indeed requires fewer observations, just because we are only observing what is really necessary. And then we also do not collide across the because of the stochastic reachability component, which is a sufficient condition in this case. But there are situations where we either run out of control actions. So this is kind of happens when we are in deadlock or we have numerical issues, or we have timeout from the SQP solver. But in general, what I want to kind of let you guys take away from this is that we can do motion planning under uncertainty and account for this duality aspect to help better sense that better sense obstacles when there's uncertainty. As next steps, we are also considering using Bayesian models to generalize beyond the Kalman filter approaches and as well as help us go beyond the obstacle motion that we are currently considering. This paper was accepted at TRO recently, and an archive paper is here as well. All right, I'll stop here to see if you guys have any questions.
So one question: how fast you can solve the optimization problem for this one? I think. Oh,
this is the current. This right now shows the entire SQP solution and the last project that we solved.
Is it possible that it fails because of the ambient large velocity?
No, I think you are asking the right question. Like it did indeed fail. We had timeouts because we were a bit aggressive, because we wanted to maintain the control frequency for I think around 5 hertz, if I remember correctly. So that definitely put a strain on the solver. But as you can see, most of the time we are quite under. And this is again a grad student's code. So if you optimize it, we expect it to be better. And this was implemented in Python too. So going to C, for example, could also definitely make improvements.
if it couldn't solve the problem in time, do you have another strategy to do? I mean, that if you can optimization.
Right now, I don't think we have another strategy because we have to solve the motion planning problem eventually, right? So yeah, I don't know if we really have an alternative solution to that. What we're hoping for is, or we did do that as well, is we were maintaining the buffer of the past MPC solves. So like there were of course situations where we could be timed out. So even though we timed out these many times, it's not like we actually had to stop the solution. It would then go back to this case. This is where the real problem comes, where we used all the past MPC solves, and the problem, just because of the non-convexity or non-linearity, is not able to converge for the 10 time steps that we have in our buffer. So this happens more rarely. So like this is one iteration of some very long iteration among 100 trials. So it's quite rare, but then we can't get guarantee that that will not happen. It's a good question. Yeah.
In those cases where you don't converge to a solution, do you know that a solution exists and you're just not able to find it numerically, or is it possible there's no solution?
I believe a solution should exist because we are not moving very fast. So like now that I'm thinking about it, we could always solve for a less aggressive objective, like maybe try to stay at its own place kind of a thing. But the issue at the hand is the obstacles are not under our control. So we had like a pre-planned trajectory with perturbations associated with it. So even if we stay at our own place, it could mean that obstacle could come and hit us. And partly why a solution could not exist is the fact that when you use stochastic reachability the way we have posted, we would be using a sufficient condition. So we are additionally adding conservativeness into the problem. So even though an original problem might have a solution, our subproblem could be conservative and just for the sake of tractability may not permit a solution. So there are a lot of moving parts in this case.
Yeah, okay, thank you.
Great. Thank you for the great questions. This is great. So since you guys have been asking questions, I will just quickly touch the last topic as well on the abort safe spacecraft rendezvous problem as well, and try to wrap up it in 5 more minutes. So in this project, we are interested in, as I briefly alluded before, doing safe rendezvous where there could be potential for failure. So an application that is of interest to us is when you want to rendezvous with an international space station, for example, we do not want to collide with it in case of a failure on our spacecraft. So this solution requires us to be careful on the rendezvous trajectory that we plan. And we could have multiple types of failure. We could have a complete loss of failure, which we call passive abort safe trajectories in the case where we can divert safely. Or if we could have a partial loss, where we could have, for example, redundant thrusters on the spacecraft, which can kick in the event of a failure. And all of this has to tackle an uncertainty coming from both activation mismatch as well as navigational errors. So there are some approaches that tackle this problem under a simplified setting where you either have passive abort safe, where there is no uncertainty, or when you have the case where you compute explicitly the divert trajectories, which comes at a very computational cost. What we use in this approach is stochastic reachability and constraint control to avoid having to do explicit computation while tackling the uncertainty aspect as well. So in this case, we use a combination of stochastic viability and trajectory optimization. So if you are not familiar with stochastic viability sets, what we are interested in is, given a collection of target sets, we want to identify this blue set from which a desired level of probabilistic safety is satisfied. And for the keep out for this problem of abort safe rendezvous, we have this keep out set. And the way we do it is by splitting it into 4 different half spaces and then computing the stochastic viability set of staying within those half spaces. We need this because the stochastic viability computation right now is best suited for convex sets, avoiding or reaching convex sets. So in this work, we computed inner approximation of these viability sets. That way we can ensure that staying within this inner approximation continues to keep us safe in the true problem aspect. Our approach is amenable to offline computation. So we actually compute these sets offline, and then online, the system just tries to stay in these sets. And what we have a guarantee is that as long as you stay within these sets, there is an abort control law, which you can also explicitly compute that will keep, can allow us to divert safely in the event of a failure. And then finally, we use a model predictive control to enforce the safety. Because there is this optionality component involved, we use a mixed integer quadratic program to solve for this different options of the stochastic viability sets. You could, for example, convexify by considering only one of these viability sets staying within that, in which case this problem simplifies into a convex quadratic program, which you can use. So in this last slide that I wanted to kind of highlight that we tested this on a numerical solution where we indeed get the stability that we were looking for. So we indeed get the safety that we're looking for. However, the set computations do require use of MPT and multi-parametric toolbox, which has some numerical issues that come about when you do the set computation high dimension. So in future, we are looking into improving that, and we're also considering time varying dynamics that might arise. In the example that we consider here, it was simple LTI system. It could be LTV systems in other orbits as well. And that pretty much concludes my talk. So I've kind of given you a brief overview of my work in safe RL-based multi-motion planning, safe planning under constraint control sensing, and abort safe rendezvous. So at this point, I'll stop here. I'm happy to talk about these topics more or other topics that I could not touch in global optimization and data-driven control. If you have any questions or if you want to just talk, please reach out to me on my email. Thank you for your attention.
Well, thank you for such a great talk. Very, very exciting. Questions? Comments?
I have a question about the reinforced learning part, the first part of your talk. Like, since you said it's motion planning method, do you have any like theoretical guarantees? Like
Okay.
units?
So we have theoretical guarantees of the following flavor. That means I don't have it, I think, in this case. Let me. No, this is not what I want. So the main theoretical guarantee that we have is the recursive feasibility on the safety filter side. So what I mean by that is when we use the safety filter in conjunction with the reinforcement learning component or reinforcement learning problem, the overall system is guaranteed to keep our system safe. That's the one guarantee that we have. Additionally, we have a secondary guarantee that whenever we start this problem from a feasible space, because of the way we construct our problem, that trajectory will be eventually stable, which would mean that our trajectory will be tracked well, and therefore the RL component is not going to introduce instability into our problem. So this is piggybacking of existing reference governor style formulation that we use in this problem.
Sorry, I didn't hear your first guarantee. The sound is.
Sorry. The first guarantee was on the recursive feasibility on the safety filter side. So that is basically meaning that if we start from a feasible solution, from a configuration where we are not immediately in collision, our safety filter will continue, because of the use of terminal constraints, can continue keeping us safe.
Okay, so is there any cases that your reinforced learning had failed to find the solution? The motion planning fails.
So the thing is, what do you mean by fail? Maybe.
Like didn't get us motion plan, like
So
didn't.
Sorry, go ahead.
I just say you say like motion planning module just doesn't provide a motion plan at all.
So that doesn't happen because because of the formulation of the RL block. RL block needs to just spit out a reference target, and this reference target is deviation. Essentially, the RL action is the deviations from the target itself. So if the RL block is actually not spitting out anything, it's equivalent to saying RL model is saying that go to the target directly. So RL block is always kind of correcting or pushing the agent either towards the target or maybe some perturbation of the target. And that perturbation is what allows the RL block to, when it is being trained, to avoid static obstacles in the beginning, but it doesn't account for the multi-agent aspect then. The safety filter then comes in, ensures the guarantees safety as well as the inter-agent collision avoidance.
Do you assume, sorry, maybe I asked too many questions, but do you assume that the obstacles is convex?
We did use that assumption implicitly in our experiments, but our approach doesn't need that as it is, because the RL block in itself, we would be treating it as the way we encoded it is using shaping the reward function to maintain distance. So I guess even there, to compute the distance tractably, it will be nice to have it convex. But if it is not convex, you could maybe construct a ball around it, which makes it convex, for example. So that's one aspect where I think not having an assumption of a convex obstacle will become an issue. And on the safety filter side, we're anyway convexifying at the end because you have a non-convex constraint to begin with. So whether it's convex or not doesn't really play a big role.
Thank you.
Yeah. Thank you for the questions.
I have a question. Which of the approaches that you use for safety do you think it has better result?
So all of the approaches that I've used underneath the hood uses some form of reachability, which I think is the best way to guarantee safety. That said, theoretically, reachability is really great. Practically, right now, the biggest issue is computational tools impose that the dynamics have to either be linear, sets be convex, and things like that. There are some works that are kind of pushing the envelope to go beyond that, but it's still not yet at the place where we can get real-time computations with reachability. And that I think is where an exciting active area of research is happening. But I am definitely sold on the fact that in order to get guarantee safety, we need reachability theory.
Thank you.
So I guess I'm coming back to, I don't know if we discussed this before, but coming back to issues on essentially topological abstractions of feedback control. Like if you were to have, like in your examples, or in the very nice experiment you have with multiple drones, you have some sort of situation typically where one of the vehicles will face an obstacle. It could be another vehicle, it could be something fixed, right? And it has this opportunity to go around the obstacle, let's say around going left or going right? So you end up with this partition of a static space that we have identified to be a partition that leads to non-smooth feedback. Because essentially, as I said, there is a set of points where from one side of the set of points or the plane, you go left and the other one you go right. So that kind of kills, to some extent, robustness for most of the optical avoidance algorithms, unless they have some sort of memory, or what we do is to encode that memory in a hybrid model. So, and then when you do that, then you can argue something about robustness. But I'm not arguing that there is something, terribly wrong, but what I'm saying is once you start proving things of this type of systems, then there are these obstacles that I think that are unavoidable unless one handles them with some sort of memory-based controller or hybrid, I would say.
Definitely,
So,
definitely. I totally
so
agree.
have you ever faced any of these issues numerically? I
Yep.
mean, these disturbances might be difficult to find. I mean, but one can craft them, but that doesn't mean that they will appear naturally.
So one flavor, so we definitely have the issue of if we don't have the terminal constraints. So the terminal constraints essentially is allowing us to keep track of this memory that you were referring to, Ricardo, because we are essentially saying that our MPC plan that is generated by safety filter should keep the drone, each of the drone in a configuration from which it will be safe forever. But there, the safety is from the interagent and the collision agent obstacle avoidance point of view. And that safety makes assumptions on the way these move. So while we don't see it in practice, I don't think I can guarantee say that getting robustness is something that is a given in these approaches. We definitely need some more research on that topic, I think. I don't know if there's a clear answer for that yet.
Yeah, I see how that could work. I think this is something. So could you send us the link to the paper that does this RL with safety?
Yep. Yes.
I saw it on one of the slides, but I wasn't able to catch it.
No worries. I can email it to you, Ricardo.
Okay.
I'll email all the three the papers covering the topics as well.
Perfect. Other questions?
I have a question about that. You solved the, I think, RF problem in a centralized fashion and then decentralized, if I understand it correctly. So what is the change of performance if you going from centralized to decentralized?
So the decentralized work is something that we still we haven't published it yet. We're working on it. But we have almost finished the experiments as of now. The main difference is the moment we go from centralized to decentralized, the safety filter becomes more conservative.
Okay.
And that means that we will have more situations where our combination of RL plus safety filter doesn't find a solution, whereas the centralized can find a solution. But there's a trade-off, right? Like centralized assumes a lot. It means that it can talk to everyone. It can also force everyone to do everything, whereas decentralized makes much less assumptions on that.
And also in decentralized, each agent sends the distance between. I mean, do they talk to each other or just?
So the way we have posed the problem there is we actually have a communication radius around it, and we can only sense other obstacles within that radius. Communication and sensing radius kind of thing.
I just have a quick question about the planning. So do you consider the dynamics of the drones, or just like waypoint?
So right now we abstracted that problem to make it tractable. So we only consider like a double integrator model for the drones.
Gotcha.
And then let the low-level controller. We used Mellinger's controller that comes with Crazy Swarms, a package for these Crazy Flies, to track those waypoints themselves.
Okay, so for the planner part, it's just double integrator dynamics, right?
Yes.
Gotcha.
And also I should point out that because we have process noise incorporated into a double integrated model, we are roughly accounting for tracking errors. I won't say anything accurately, but we have some robustness kind of baked in from there. But as you can imagine, this is very hand wavy to say that we are accounting for exact tracking errors.
Thank you.
Yeah.
All right. Well, I think we have probably abused our speaker So
No, not at all. Thanks so much for the questions. You guys have been an amazing audience. Thanks a lot.
well, that's the interest, is to have a exchange and learn how things are being done on your end. Very, very interesting. Okay, with that being said, unless there is any other question, we will wrap it up.